Chapter 1's lecture, this will just be part 1 for you guys. I will not get through it today. I'm hoping we can get through it, though, in 2 parts for my A days. So this class and next class. A lot of this is review. You guys, you know that. So really engage yourself and listen carefully, okay? And if you are having any difficulty with understanding what I'm saying, you need to go take time with that book and reteach yourself, or get online, or come get some help from me, because I will not lecture all of this. This is stuff you've learned from middle school, okay? And you'll see what I mean, hopefully, as I start clicking through these first slides. So I expect that you guys already understand atoms, molecules, and compounds. You guys should know what elements mean. You guys should know what atoms are and the 3 parts of an atom. There is in your appendix, the first appendix, I think, in your book, that yellow section, a table of contents. You might not have been aware of that. So it's back there to help you. Let's review just a little bit with atomic number and make sure we know that. I thought I had this on. Okay, perfect. So since it can't see my whiteboard, I'll use the Elmo a lot back and forth. So for example, oxygen. Before we give the perfect example here of oxygen, first, what is the atomic number represent? Just yell it out. Number of something, but not atoms. The number of, yell it. Protons, okay? Now, normally, this number equals the number of what else? Electrons and neutrons. However, these vary. This is the number that defines the element of that particular atom. So if we look in the book really quick, or maybe some of you know it, what is the atomic number of oxygen? Just yell it out. 8. We think it's 8. That sounds right to me. So the atomic number is 8. So how many protons does oxygen have? How many electrons? How many neutrons? Okay, but the electrons can vary because of bonding. This is what makes elements reactive. So they share them. If they want to get really close to them, they kind of give them away. If they want to get really close to them, they might take them. So this varies. I will talk to you more about varying the neutrons here in a minute. Okay, the other thing that you can figure out just by knowing your atomic number, which you don't need to memorize, you can look them up in your periodic table, is what is the mass of oxygen? You should be able to calculate that right now. I heard it, yeah. Okay, so hold on. So where are the protons in an atom? They're in the nucleus. Where are the neutrons in an atom? They're in the nucleus. Where are the electrons in an atom? They're flying around in an orbit. They call it an orbital or a shell or a cloud. Now, and there's going to be the same amount of these until it bonds. Okay, now, what makes the mass of an atom? The nucleus. So how many protons are in this nucleus, supposedly? Protons. How many neutrons? 8. They weigh about 1. There's some digits back over here, but you could see it's about 1 atomic unit. Both of them weigh about the same, protons and neutrons. So therefore, what's the mass of it? Beautiful. 16 is the mass. Okay? Now, we'll come back to that. The electrons are there, but they are insignificant. They're over in the end. They're like 0.000, I don't know, 167, something like that. So you round them away. They're insignificant. Okay, so back to here. Again, if you are confused on any of this stuff that I'm going to go very quickly through, you need to read more thoroughly or come get some help. So here is a what type of molecule? What's the formula? H, 2 H's and 1 oxygen. So H2O, and some other examples are right there. Okay, so I went through that stuff. Now, this is new, and I want to make sure you understand this. Write down CHNOPS. CHNOPS. It's a nice acronym for you to remember what organisms are made up of. CHNOPS. Okay, not the alcoholic schnapps. I think that's an SCH or something. It's just a word made up to remember this. Now, I'm going to ask this question. I'm expecting fully to get the wrong answer, but that's okay. We're going to get this misconception stomped out right now. What are we made out of? Okay, I'm hearing both. I'm hearing let's see, I commonly hear that we're made out of, what did I just hear? We are made of atoms, so what's the molecules we're made out of? I hear water most of the time. Now, think of this building, this big, huge building, both sides, all connected. What is this building made out of? Concrete, wood, what else did I hear? Okay, drywall, all this stuff you're telling me this building is made out of. I agree with you. Now go back to let's make this an analogy back to the body. Are you guys really made out of water? So if you were going to give me the same sort of analogy answer with the building, what would you say the building was made out of? Or what is this building full of? People, yeah. What else? What takes up most of the mass or the volume? Air. Do you see my analogy? This building's not made of air. It is containing full of air. There's a lot of air in the building. This is the same analogy to the human body or all bodies. Okay? Even plants have a lot of water in them. Are they made out of water? No. Do they have a lot of water in their spaces? Is the water necessary? Okay, so I'm now at the atomic level. Yes, we are made out of cells, so what are the cells made out of? And what molecules are they? I heard some of you answer, they're carbon-based molecules. Okay, so I want to make sure you guys write that down. Organic is what I'm looking for there. I know this thing is a disaster. I will finish, no matter what, I will finish your guys' supply check next class, so make sure you're ready for that. Okay, so anyway, organic. Organic means that it's made out of what? Carbon, okay? All life on Earth is made out of carbon molecules. The carbon is the skeleton. There's just a real simple skeleton there. And to it are bonded what other elements? Look at schnapps. We got a lot of oxygen there. We got a lot of hydrogen there. And it's because that you have OHs and H's. And you can see there are, on these carbon molecules, there are a lot of H's added to it and even oxygens. So when you see we have mostly oxygen in our molecules, it's not in the water. It's in the carbon molecules. Okay? Now, you're going to memorize this right now. So you got schnapps. What's the C stand for? The H. The nitrogen. Oh, the N. O-P-S. Okay? You need to know that. Now, that's not everything. What's this last thing say on your pie chart? Trace elements. That's things like sodium and chlorine. You need these things, but very small amounts. Too much of it hurts your heart. But you need sodium and chloride to make your nerves work. You need iodine. You need iron. You need these, but really small amounts. Okay? All right. So moving on. Okay. Again, we've went over this. Electrons, protons, neutrons. Where they're located. And again, we went over that when I was writing on the Elmo. There's nice reviews. If you read these carefully, it'll also help you. Okay, so look right here. First, before even getting to the isotopes, what's wrong with this image? There's a very simple typo there, and I decided to leave it so that you would notice it and fix it. This is carbon. How many protons does it have? How many neutrons? How many electrons? So they all have 6 in the little graphics. So fix one. There should be another electron right there on that outer shell. So the outer shell is where there's the reactivity. The shell would like to be filled. How many electrons are in the second shell? How many when it's full, how many should there be? 8. So this is why carbon is so important, because it will make 4 bonds. It makes a great backbone. It makes a great skeleton. Okay, the other reason why I have this up here is to make sure you understand what isotopes are. Isotopes vary in the number of what? Protons would make it a different element. Electrons are just the bonding stuff. Neutrons. Okay, you've got to know that. Now, when we name our neutrons, we do it with the atomic weight. Do you guys see that? This is actually carbon 12. This is carbon 13 because how many neutrons does it have? And you add them up, right? And carbon 14, how many neutrons? Okay, you've got to be very familiar with your isotopes. Your isotopes are radioactive. They're not stable. They give off little waves, which actually can be harmful to cells. The small radioactive ones, like carbon 14, don't bother us really. They're not as unstable enough to cause any damage compared to plutonium and radon and uranium that have hundreds, and their mass is well over 200. And they're giving off a lot more waves, which can hurt cells, and that's what we call radiation. Okay, again, chemical bonds. I'm hoping you guys are very familiar with this. I'm hoping you're very familiar with balancing equations. We won't do it very often, but I'm hoping you know how to do it. So real quick here, how many hydrogen atoms are in this equation on the product side? It is 4 because there are 2 water molecules, and each water molecule has how many hydrogens? 2. So 2 times 2 is, okay, go to the reactant side. How many hydrogens do we have over here? 4. Okay? So make sure you know that. That's called stoichiometry, and it has to do with this law of conservation of mass. We'll get to that in a minute. Okay, so enough with the atoms. Moving on to life now. So the basic unit of life is the cell. Beautiful. And in the cell, there are chemical reactions going on constantly. We have chemical reactions going on for 2 reasons within cells. And this is for all life, because all life is made out of cells. The main reason we have chemical reactions going is to form what? New molecules. So back to that human growth hormone. It is a very large molecule compared to molecules in general. It's a huge protein. That is made by the cells in chemical reactions. Okay? And even breaking down water or forming water. Getting some carbon backbones, making phospholipids for the membranes. So the cell is constantly doing chemistry to form new molecules. What's the other reason that chemistry is involved? What else does the cell get by breaking bonds, for example? Yell it out, what? Well, I thought I heard it. I mean, when you break bonds, when you start a fire, what do you get? Energy. So that is the other reason why chemical reactions are occurring. Because we have all our energy is stored in chemical bonds, and we have to break it to free that energy. Okay, let's listen to this.
The law of the conservation of matter states that matter is neither created nor destroyed in chemical reactions. When 2 molecules of water receive enough energy to start a chemical reaction called the activation energy, 2 molecules of hydrogen and 1 molecule of oxygen are produced. Note that the number of hydrogen and oxygen atoms remain the same before and after the reaction.
Okay, that is the law of conservation of what? Mass or matter. Is there another law you guys are familiar with? Of energy also, okay? But we're going to talk about the matter one right now because we're talking about chemical reactions. The energy cannot be created or destroyed also, but you're talking in the whole universe. The Earth is almost a completely closed system, so whatever matters on Earth, it stays on Earth. There's a little bit of introduction from like meteorites and things like that, okay? And if we were to get hit by an asteroid, a big one, we could possibly eject some matter out into space. But in general, we're a closed system, so all of those are balanced. Okay, the other vocab word that you need to know is activation energy, okay? And if you go back to that equation, right here it says electric energy. It showed a spark in the previous thing. You do need a little bit of energy to get any reaction going. Then normally the reactions will break more bonds and release more energy. Just if you think of a simple match, and you just, that energy motion, you just move that I can't talk. You strike it. Yeah, just that energy that you have moved, you have started a bigger chemical reaction because now it lights up and it moves and it gives off a lot of heat. Okay? All right, moving on to ions and to bonds. Again, I'm going to move into high gear. I'm going to go quick again. You should know your bonds. This is the strongest bond. You might not have been aware of that, and that's because of what happens between the electrons. So sodium is a +1. It has one electron in its most outer shell. Is it happy like that? No. So it'll get extremely close to something else that wants it, that it can give it away. Chlorine has 7 in its outer shell. It would like 1. Now, they don't really lose their electrons, but they are so close together that the bond is really strong, and then that little bit of energy is being utilized to stabilize the chlorine. And the sodium is more stable because it's not taking advantage of that electron. You see this as very strong because they're crystal strong, like a salt crystal. Yeah, okay? So that's ionic bonds. The next type of bond's called covalent. What's the key word there that you want to remember so you can find it on a word list? They share their electrons. They don't give them away. They don't take them, gain or loss. They share them. So then they're both equally close together, and that you can break these covalent bonds easier than ionic bonds. Okay, water's for example of one. All the carbon molecules that make you are another one. Okay, so you're going to go ahead and in the back cabinet, you're going to grab the model kits. One per table. Hop up and get it, please.